Welcome students, we want to discuss about partial derivatives in this lecture. Before that, let's read the quote. Young men, in mathematics you don't understand things, just get used to them. This quote is by John von Neumann. Neumann was an American mathematician from 1903 to 1957. So he really lived for a short time, 54 years, but Neumann is in everywhere, all right? So from functional analysis to algebraic geometry, quantum mechanics, Neumann is everywhere, all right? So he's a polymath in true sense. So, so with that, let's start with the definition of partial derivatives. So what are partial derivatives? So word partial means you're not doing some complete derivative, but you're doing some partial derivative, all right? So let's see where the idea comes from. So you have f of x, y. So recall, if you had y equals to f of x, then you saw the change of y with respect to x, the instantaneous rate of change of y with respect to x was the derivative dy by dx. So if you call this as z now, you can change z with respect to x or with respect to y, right? So change in z with respect to x, change in z with respect to y. So that will give rise to partial derivatives, okay? So let's formalize this. So the partial derivative with respect to x given by partial derivative of f with respect to x. There's another notation. You basically write f, x, y, and do a small script of x here. This is basically limit as h goes to 0, f of x plus h, comma y, minus f of x plus h over h. So if you notice this, your y is as if it's a constant, and your x is changing. So partial derivative of f with respect to x is this limit. Similarly, partial derivative of f with respect to y is written by another notation is xy, f of x, y, limit as h goes to 0, f of x comma y plus h. So you're changing y now in this case, minus f of x, y over h, provided these limits exist, right? Provided they exist. If these limits do not exist, then the partial derivative is not defined, right? Provided these limits exist. So these are your partial derivatives. Now, how do they geometrically look like? So let's take a point here. Let's fix a point at the bottom. Call this as AB here. So let this point be AB. Now, what we do is we are keeping y equals to b constant. So this plane is y equals to b. Plane y equals to b. So now when you cut your surface S, this surface S is defined by f of xy equals to z, right? So this is what the definition of your surface is. F of xy equals to z. And now you're keeping your what? You're keeping your y constant. That means y equals to b. And when you do that, you get this curve on your graph. And corresponding point on the surface is this point A. So now what you're doing essentially is when you're looking at f of x, fxy, that means partial derivative of f with respect to x, you're looking at the slope of the tangent line at this point. So you're looking at the slope of the tangent line, this point. So this corresponds to slope of this tangent line is, the slope of this tangent line is partial derivative of f with respect to x evaluated at AB. Similarly, we can define partial derivative of f with respect to y at AB. So this is what the partial derivative is. Now, the question is how to calculate the partial derivative. So if you notice the following here, in this case, when you're computing partial derivative with respect to x, or for that matter, when you're looking at partial derivative with respect to x, your y was constant. Yeah, your y did not change. There was only change in x. So this gives us an algorithm to compute the partial derivative with respect to x. Then you regard y as a constant and differentiate only with respect to x. Similarly, if you want to compute partial derivative of f with respect to y, then you regard x as a constant and differentiate only with respect to y. Okay. So these are some rules of partial derivative, namely partial derivative of f plus g with respect to x is partial derivative of f with respect to x plus partial derivative of g with respect to x. This is what is called a summation rule. Yeah? It's very similar to the derivative rules you had for the function of one variable. Now, similarly, you have constant times f of x. The constant can come out. So you get c times partial derivative of f with respect to x. You have product rule the same way. Partial derivative of fg with respect to x is partial derivative of f times g plus f times partial derivative of g with respect to x. Similarly, the quotient rule is exactly the same. Instead of d by dx, you have partial derivative with respect to x. I mean, of course, provided g is not 0. Now note that similar rules are for partial derivative with respect to y as well. Okay, so let's do this computation and things will become clearer. So partial derivative of z with respect to x. So this is same as partial derivative of this with respect to x, y sine x, 1 minus cos y. Now notice that cos 1 minus cos y has no x in it, so it's a constant with respect to x. So I'll take 1 minus cos y out, partial derivative of the inside part. This is going to be 1 minus cos y, partial derivative of e to the x. Now I'll use the sum rule. So e to the x derivative is e to the x. Y is a constant, so it comes out. Partial derivative of sine x with respect to x is equal to cos x. So this is your partial derivative of z with respect to x. Now let's look at partial derivative of z with respect to y. Now in this case, both numerator and denominator are functions of y. So I can't take it out as a constant when like I did here. Here I will have to employ the quotient rule. So I have 1 minus cos y the whole square, 1 minus cos y as it is, partial derivative of with respect to y of e to the power x minus y sine x minus e to the y minus y sine x times partial derivative of 1 minus cos y. Yeah, this is purely quotient rule written in terms of y. Now let's do the computation. So I have 1 minus cos y, partial derivative with respect to y of e to the x is 0, y is 1. So sine x is a constant, it comes out. So we have minus sine x minus e to the x minus y sine x. Partial derivative of 1 with respect to y is 0. And then we have cos y derivative is minus sine y with respect to y. So it becomes sine y the whole divided by 1 minus cos y the whole square. So this is the partial derivative of z with respect to x, z with respect to y. Okay, now let's look at the following problem. The volume in cubic meter of 1 mole of an ideal gas is given by V equals to 82.06 T over P, where P is the pressure in atmospheres. T is the absolute temperature in Kelvin. So Kelvin is degrees Celsius plus 273. Find the rate of change of volume of 1 mole of an ideal gas with respect to pressure and with respect to temperature when T is 300 K and P is 5 atmosphere. So what is the problem asking us? The problem is asking us rate of change of volume of 1 mole of ideal gas with respect to pressure. So first we are computing partial derivative of V with respect to pressure. And we are evaluating at what point? At 300 is the, so I want to write this as V of Tp. So my volume is a function of temperature and pressure. So what I'm looking for is partial derivative of V with respect to P evaluated at T is 300, P is 5. And then the second one, what we are looking for is partial derivative of V with respect to what? Respect to temperature, again evaluated at 5. So now let's compute this. So first we'll compute partial derivative of V with respect to P, and that we get as following with respect to pressure. So we have the constant, we have by P of 82.06 T divided by P. Now the numerator is a constant because there's no P there. So times T, P of 1 by P, and derivative of 1 by P with respect to P is minus P square, 1 by P square with the minus sign. So this is going to be T multiplied by minus 1 by P square. Therefore, this is going to be the change in the volume with respect to pressure at 300 Kelvin and 5 atmosphere pressure is going to be 82.06 times 300 divided by minus 1 by 5 square. And this is going to be 984.72 mole per atmosphere. Right? Similarly, dV by dt. So now we need to compute dV by dt at 305. So let's first compute dV by dt. That is going to be d by dt of 82.06 T divided by P. So everything will come out, by everything I mean 82.06 and P, and derivative of T with respect to T is 1. So this is your partial derivative, and then when you are evaluating it at 300,5, this is going to be 82.06 divided by 5, and that is going to be 16.412. So again, moles per Kelvin. So mole per Kelvin. Okay, so this is the rate of change of volume with respect to pressure and temperature. Now we can talk about higher order partial derivative. So first you start with F. Then for F, you can take the partial derivative with respect to X. which can be also written as dou f by dou x. And then you can take partial derivative with respect to y, which can be written as also as dou f by dou y. Now note that this is also function of, but fx is going to be function of x and y as well. So we can take another derivative of this with respect to x, which will give you dou square f by dou x square, and that is also written as fxx. Now this is something new because we have mixed derivative in this case, because after all, partial derivative of this guy is also function of x and y both. So we have mixed partial derivative, that is dou square f by dou y dou x, and when you write it, it's written as fx, and then you take derivative of that with respect to y, and that is written as fxy. Similarly, for this guy as well, we can take partial derivative of this with respect to x, that is also written as dou square f by dou x dou y, or it's fx fy of x, that is written as f of yx. Or if you took partial derivative of this with respect to y, you get square f by dou y square, which is fyy. Okay, so there are mixed partial derivatives here, right? Derivative of y with respect to x, and derivative of x with respect to y. So then the question is, are these equal? So are these two quantities equal? They are not always equal, but most of the times, if your function is nice, they are equal. What do you mean by function is nice? So that is given by Clarion's theorem. So Clarion's theorem tells us the following: if f of x y and f of yx are continuous on a circular disk centered at point AB. So if you have a circular disk centered at point AB, and in this region inside, what you have is that your fxy and fyx, these mixed partial derivatives, are equal inside if the mixed partial derivatives are continuous. You don't need the equality. fxy and fyx are continuous, then we have fxyab is fyxab. That means that the mixed partial derivatives xy or yx are equal. Well, very neat. So let's look at that by an example here. So let's look at the following problem. Find the second and three order partial derivatives of this function. All right. So first find fx, that is going to be 3x squared. Again, minus 3x squared will become minus 6x. Y, the constant, comes as it is, multiplied, plus 0. Secondly, we get partial derivative with respect to y is going to be, now this is 0 with respect to y, so because x cube is a constant with respect to y, so we get 0 minus derivative of 3 minus 3x squared comes out as a constant. Derivative of y is 1, so 1 plus derivative of y square is 2y. So this is your first order derivative. So first order derivative. Now for second order, derivatives, we'll use the first order derivatives to construct these. So dou square f by dou x square, or partial derivative of f with respect to this, can be written as the following. This is same as partial derivative of, so now partial derivative of f with respect to x is already computed here, so 3x squared minus 6xy, that is going to be 6x, and the derivative of minus 6y with respect to x is minus 6xy with respect to x is going to be, derivative of x is 1, 6y is a constant, comes out. Similarly, we have partial derivative of f with respect to y and x. So first this is same as taking y, derivative of x, dou f by dou x. So we have this guy is 3x squared minus 6y, and we are taking derivative of this with respect to y now. So the first one is 0, second one will be just minus 6x. Similarly, partial derivative of, now I'm looking at the other one. So y is 3x squared plus 2y, and with a minus sign, right? And that is going to be minus 6x. So from 1 and 2, you see that they are continuous and they are equal, right? This proves, this doesn't prove Clarion's theorem, but this is an example of Clarion's theorem. All right, now one more partial derivative, second order derivative left. Square, that is going to be y of dou f by dou y, which is to be minus 3x squared plus 2y, which is going to be 2. So these are second order partial derivatives. Now for the third order partial derivatives, we have to compute all the mixed ones. So we'll start with first cube f by dou x cube is same as partial derivative of this guy, which is same as 6x minus 6y, which is going to be 6. So third, similarly we have now take each of these and take derivative of them with respect to x, and then take derivative of them with respect to y. So that's what we are doing here. So I will do one more computation and leave rest as a homework. So we have this came out of taking what is dou f by, so this part is already computed, minus 6x, that is going to be minus 6. Let's do one more. Now I'll take this guy and take derivative with respect to x, so we get x dou y dou x y is going to be, and then we have to take partial derivative of this with respect to y, so we get This is going to be minus 6x, which is minus 6. Okay, so rest you can compute, but here, food for thought. Why are they equal? And then the answer should come from Clarion's theorem. Okay, all right, so we can continue this and finish this off. Okay, so this is about computing partial derivatives. So now this game can be extended to function of more variables, right? This can be extended to function of 3 variables, 4 variables, n variables. So again, fxy is you change in fx of xyz is going to be you changing with respect, you're only increasing in x, you're seeing change in x by keeping yz constant. And the computation is exactly the same. You basically have to do the computation. So suppose I want to compute this. So first I'll compute. So first I'll compute the first one here, starting from left or right to left. So let's compute this. In this case, I have to treat y and z are constants. So they come out, and derivative of this is 1. Now I want to do the derivative of yx, that is same as taking the previous one, taking derivative of this one with respect to y, going to be feed from the previous one, 1 plus y. So I'm going to write it at y plus 2z to the power minus 1. Now I can use this as a chain rule. Note that 2z is a constant with respect to y. So this is going to be minus 1 by y plus 2z the whole square times partial derivative of this with respect to y, which is just 1. So we get minus 1 by y plus 2z the whole square. Now let's look at the next one. So we have the third order derivative of z, y, and x. This is going to be partial derivative with respect to z of partial derivative, second order derivative with respect to y and x. Then we get minus 1 by, again I'll write it as a power because that's easy way to 2. Now here y is a constant with respect to z. So this is going to be, so minus 1 times minus 2. So 2 y plus 2z to the power minus 2 minus 1, which is 3, times partial derivative with respect to z of inside 1. Yeah, this is a consequence of chain rule. So we have 2 upon y plus 2z to the power 3 multiplied by derivative of inside, which is 2. So note that chain rule also naturally extends to this setup. Only thing you have to be careful about is when you're doing with respect to x, then yz is constant. If you're doing with respect to y, then x and z are constant, and so on and so forth. Okay. Let's look at the following problem. So verify that this function is a solution to 3-dimensional Laplace equation. So since this equation has derivatives in it, it is a differential equation. Since these derivatives are partial, these are partial. This equation is a partial differential equation. It is one of the important differential equations. It's called Laplace equations. So let's work it out and see if it is indeed true. So what is u? U is x squared plus y squared plus z squared to the power minus 1 by 2. So let's compute partial derivative of u with respect to x. That is going to be half x square plus y square plus z square times to the power half minus 1, which is minus 2 by 3, multiplied by derivative of inside. So let me just write down that step. X square plus y square plus z square. And then this partial derivative of this guy, this part with respect to x, is 2x. So we get minus 1 by 2 times x square plus y square plus z square to the power 3 by 2 times 2x, and that can be simplified as x minus x times x square plus y square plus z square to the power 3 by 2. Now let's compute partial derivative of this with respect to x. So second order derivative, this is same as taking derivative of this guy with respect to x. Now here we have two functions, both are functions of x, so we'll use product rule. So minus sign outside, so x times minus 3 by 2 times x square plus y square plus z square to the power minus 5 by 2 multiplied by derivative of inside, which is 2x, plus x square plus y square plus z square to the power minus 3 by 2. Why is that? Because we have derivative of x is 1. So these guys will cancel off. We'll simplify this a bit. So we get 3x. So 3 times 2 is 6x. So and then little bit of simplification can actually show us that this is going to be minus 2x squared plus y squared plus z squared divided by x squared plus y squared plus z squared to the power 5 over 2. So if we add these guys up, so now from here, since it's so symmetric in y, x, and z, we can argue that we should be able to argue. Therefore, we have that with respect to y is also going to be the same thing, but instead of x squared, it will be minus 2y squared, x squared plus z squared divided by x squared plus y squared plus z squared to the power 5 by 2. And similarly for z as well. Yeah, so let's write that for z as well. So for z is going to be again minus 2z squared plus x squared plus y squared upon x squared plus y squared plus z squared to the power 5 over 2. Now when we add all of them up, we get, so this thing is common for all of them, right? The denominators are same. So we have minus 2x squared plus y squared plus z squared plus minus 2y square plus x square plus z square. That is from y part. And similarly from z part, we'll get minus 2z square plus x square plus y square. Now, if you look at this, this will cancel out with this and this. Then you have y square canceling out with y square minus 2y square plus another y square 0. And then we have z square plus z square minus 2z square equals to 0. So the whole thing becomes 0. This is what we needed to prove. Okay. All right. So next problem is the following. So you're given a contour map for your function f of xy. And now from this contour map, we want to compute the following. So we want to compute the partial derivative of f with respect to x at 2, 1 and partial derivative of y with respect to x with y, f with respect to y at 2, 1. So how would we go about it? So first we start at 2, 1. So when my x is 2, my y is 1. So when x is 2 and y is 1. So at this one we have y is 1. So this is a point corresponding to 2, 1. So if you look at this, it is along the line 10. So we can see that f of 2, 1 is 10. Now we want to compute fx of 2, 1. So we will move only in direction of x, keep y constant, right? So move in direction of x, keep y constant, right? Because that's what partial derivative with respect to y means, sorry, with respect to x means. Y is constant. So when we move, we reach in here, we reach f of, so how much did we move? It looks like we have f of xy here is f of xy is 12, right? So f of xy equals to 12. So now we moved here. How much did we have to move in x? So we had to move. So the average change here is so f changed 2. So delta f by delta x roughly, right? So delta f is basically 12 minus 10, which is 2. And delta x is, you can see that it is roughly, it's bigger than 5. So let's say 0.6. So delta x is 0.6. And so we get, so fx is going to be, so 2 divided by 0.6. So 2 divided by 0.6. So 2 divided by 0.6, let's keep it that. Now, so that is 2 divided by 0.6. Now let's move in the other direction. So if we look at here at this point, so 2, 1 was here. So if we move from here to here, we see that the change in the function is from 8, right? This corresponds to line 8, f of xy equals to 8. So 8 to 10, so it changes from 8 to 10, and this looks like almost 9, right? So 0.9 unit. So average change in moving x from 8 to 10. And in this case, it was average change, move in the direction of x, keeping y constant from where to where? From f from 10 to 12. And in this case, average change in moving x from 8 to 10. So f of f changes from, so your f changes from, so average change moving in the positive direction of x-axis. So moving in positive direction of x-axis, keeping y constant. Then we get delta f by delta x is going to be, so it moved from 8 to 10, right? So it moved from 8 to 10, so that is 2 units. So 2, and how much did x change? X changed like 0.9, so divide by 0.9. So therefore, it makes sense. It makes sense to take 2 plus 0.9 plus 2 divided by 0.6 over 2, average of this as your f of x of 2, 1. That is going to be, so 0.6, so we have 1.2 plus 1.8, 1.2 times 1.8 divided by 0. So 5 nines are 54 times 2. And the answer is roughly 2.8. Okay. So similarly, we can compute Fy of 2.1, and Fy of 2.1 turns out roughly to be minus 2.1. Thank you for your attention.